Okay, so in the last video we talked about two things. One's really important. It'll apply to both lenses and mirrors, is that not everything that's shiny or not everything that's clear will actually create a coherent image. In fact, one of the issues for astronomers is the fact that the air is chunky and it doesn't create a coherent lensed image of stars and planets, which is why everything looks fuzzy. But what we do know is that, and you're taking this on faith in this class, is that if something has a focus, then it will create a coherent image. So what a focus is light coming in from infinity will all go through a certain point. Alternately, you can think about the focus as if light is coming in parallel to the principal axis, then that will also, if that also goes through a single point, then that's a focus. So the second thing we showed, a little bit hand-wavy, but good enough, is that spherical mirrors, so mirrors that are cut from a sphere with some radius of curvature r, both concave and convex have a focus. So that focal length, we've got absolute value bars on this because we'll put in SIGN signs in a minute. The focal length is half the radius of curvature. So we know that our spherical lenses, spherical mirrors, later it will be true about spherical lenses, actually will create a coherent image. So no weird funhouse mirror type distortion. The thing that you see is actually going to be represented coherently after it goes through the mirror. No distortion. So now the important question is where, right? We know that these things will create a image, but I'd like to know where the image itself is. So there are two ways of answering that question. There's the idea of ray diagrams, which is pure geometry. And then there's the idea of a mirror equation, which two of the rays from this pure geometry will be used to derive this. And again, we'll go through as much of the proof as it makes sense to, so that it's almost like a mnemonic for how to use it. So what I'm going to do is start by creating a ray diagram, and we'll do this for a concave lens, concave mirror. I'm already skipping ahead to lenses. So this thing's got a principal axis. Principal axis comes and cuts the thing right in half. What a principal axis really is where I'm putting the image, object. So let me do exactly that. Let me put an object down, and then just as a more reminder, this is the radius of curvature of that lens. So you'd imagine that as being the center of the disco ball from which this was cut. And the focus is halfway in between the mirror itself, where it strikes the principal axis, and the radius of curvature, where the radius of curvature starts, the center of the lens. So this is F. Okay? And what we know from our kind of pathological example from last time is that two rays are not enough to figure out where a coherent image is formed. So we'd like to have three. And in general, we do need three rays to make a ray diagram. Remember, just two will potentially lead you astray. And the idea is we want three independent rays, and believe this or not, physicists are really lazy. We would like to have the most elegant and easy to use, easy to remember, easy to sketch rays that we can possibly dream up. So 1, 2, 3 things that come off of this object. I get to draw a ray off of the tip of this in any direction I want. The question is, what three directions would make the least work for me? Well, so number one is using the idea of the focus. So if I go in parallel to the principal axis and I strike the mirror, the whole point of the focus is that if you go in parallel to the principal axis, I will go out through the focus. So that's ray one. So in parallel to the principal axis, out through focus. Ray 2, and 3 for that matter. So there are two ways of getting this. One is being really clever about the symmetry of the lens. The other one is being really clever about the symmetry of light itself. So I don't show you where it's coming from. If I just showed you a beam of light traveling across a desk or something like that, could you tell which way the source was? Or stated another way, you see a laser pointer in one of these movies where people are breaking into stuff. Do you know which thing is creating the laser and which one's reflecting it? So that's the hint behind Ray 2. The really fancy way of saying it in Uber physics jargon is to say that light is time translation invariant, is that if this is an okay way for a ray to travel, then if I had an object here, that would be an okay way for the ray to travel. So what we can do is realize, well, what we said is the focus is defined as in parallel out through focus. What if I went in through the focus itself? How would I come out? If I thought about flipping that ray, I would realize like, oh, in through focus means I would go out parallel. So we'll do exactly that for Ray 2. So that's independent, it's coming off at a different angle, and it's easy to draw, so we love it. So in through the focus, and then out parallel to the principal axis. So that's a good Ray 2. So in through focus, out parallel to principal axis. And I'll be a little cheaty. I'll just say like P dot A for principal axis. We're going to be doing enough writing. Okay. Okay, what about 3? I need a third ray. I mean, it kind of looks like I have 2 intersecting there, but I'm not going to be fooled again. So any 2 non-parallel rays will intersect somewhere. It doesn't necessarily mean the image is coherent. So this one, there are other things that you could do, but these are really the 3 easiest. So the third one, you can think about using not the symmetry of the light, but the symmetry of the mirror. So the easiest law of reflection ray that I could possibly draw is just strike this thing right here, right along the principal axis. So this comes down, and what I know is the angle of incidence equals the angle of reflection. And the way that I could draw that really precisely is by saying like, well, this ray coming in, this is Ray 3, in between these 2. This will make a similar triangle with that. So if I trace this back to there, what I'll get is something that should obey Ray 3. And what you'll see is, especially me moving side to side, these are not very precise, but it will show that there's an image located somewhere around there. Okay, so we're about this high, that high, if I do this better. Obviously, you can tell how precise these are. If only we had an equation. Maybe here-ish? I don't know. That looks pretty bendy. And I probably had my eye guiding this a little bit. Yeah, definitely. Okay. So that's our third ray. So Ray 3. And that's hitting the mirror at the principal axis. And then not using the focus, just directly applying or appealing to the fact that the angle of incidence equals the angle of reflection, so these 2 would be equal. Okay. So I have an image. These things cross. Now would be a good time to remind ourselves and characterize this image. So to me, this looks like a real image. It's a real image because the light rays actually converge there. It's not like they appear to have converged there if I trace them back. So they actually converge. So that's a real image that's inverted. And if I use my same really fancy calipers, I get that it's maybe a little bit smaller than my object. So maybe that's a magnification of negative 0.8 or something like that. So with plane mirrors, we didn't have to worry about magnification, but now because this thing might be shrunk or stretched, this is a good time to define exactly that. So technically what this is, magnification, there are really 2 ways of talking about it. You might hear angular magnification. Technically, this is what's called lateral magnification. I think that maybe 85 to 90% of the time we'll talk about the lateral magnification. So if you say magnification, I'm fine with that. So the magnification of an image is really just the ratio of heights. So the symbol we use is m, and m is defined as hi divided by h naught. Notice that there are no absolute value bars on this. So remember, this is a sign, so this is h naught, the image's height, and this is, sorry, the object's height, and that's hi, the image's height. Because hi is flipped, this is negative. So it can totally be the case where magnification is negative. So we have two special cases to keep in the back of your mind. If m is less than 0, it's negative, then we have a flipped image. And the other thing that we can look at is the absolute value of this. So if the magnification is greater than 1, we have a stretched image. So the image has been increased in size, and if the absolute value of this is less than 1, it's been squashed down and shrunk. So maybe, roughly speaking, I would say that this, according to my ray diagram with my 3 rays, would have a magnification of maybe like negative 0.8, seems about right. So it doesn't matter if you use centimeters or meters, all that matters is that you use the same thing. So this will be a unitless quantity, the lateral magnification. And we didn't have to worry about that with plane mirrors. Okay, so that was wonderful. What we'll do in the recitation section is we'll do an example of this and dream up the 3 principal rays. And they kind of, they're not different than this. It's just we have to be a little bit squirrely about how we treat the focus for a convex spherical mirror, because the focus is going to be on the other side. So we'll all do that together in whiteboard session. Okay, so that's the idea of using just straight up geometry and our idea of the focus. So now you see why the focus is really useful. So it actually guides some of our principal rays. So what I'm going to do is redraw 2 of them, and we want to do the second thing. So as fun as this is, deep in your heart of hearts, you know that physics is going to involve numbers. So I'd also like to make a precise numerical prediction about 1, where that image actually shows up, and 2, what is the magnification of that image, or what is the image height. And to do that, we need an actual equation. So we'll sketch the derivation of the mirror equation. And I'll just kind of stretch out this picture a bit and keep 2 of the principal rays, 2 that we'll use to kind of hint at how this would work. So I'll change things up a little bit just to indicate we don't always get magnifications of less than 1. So here's a fun one. So let me have, this is my object, and ray 1 would be through the focus, out parallel. That's what it does, wretchedly parallel. And, sorry, that's ray 2. Ray 1 is in parallel out through the focus. And then ray 3 would be hit that and then go that way. And what I get is, wow, this ray diagram stuff is pretty efficient. Okay, I actually drew all 3. This ray diagram stuff is pretty efficient, and I get an image here. So this would be hi, and that would be ho. And secondly, what I can do is I can pick out 2 of these. So I'll pick out this part of the ray and this part of the ray. And what I've made is 2 similar triangles that will let me sketch the proof of the mirror equation. So looking at this triangle in black, and don't worry, I'll redraw it because it's a little bit scruffy. So we have the object height, and we have DO, and that's a right triangle because the object is coming right off the principal axis, and that's theta. And then here with the image height, it's the same angle theta, and this is also a right angle. So I have 2 not equal but 2 similar triangles, so hi, theta, and di. So these are similar, which means that this is true, is that the ratio hi over h naught is equal to the ratio di over d naught. This is always positive, this is always positive. These might be switched in sign, so just to be really clear about it, I'll throw away the potential negative signs here. So in magnitude, this is true. So that's just from our 3rd principal ray. Okay, so it's a little bit more awkward, but I could include the focus, and I could draw a second set of triangles like this. So using ray 1 or ray 2. And mostly the point of doing this is to indicate like how these proofs work. The answer is geometry, which is probably not a surprise considering we're talking about geometric optics. And what you get is another relationship that looks a little bit funkier. Got that backwards. Teach me to look at my notes. So, and again, we might have an absolute value bar there because this thing might be flipped. So we get a second set of similar triangles, and then we just put them together with some algebra. And this and this. This is everything you need to know if you were to go through and like count all the knowns and unknowns, but there's a much nicer way of expressing these. One is that we can figure out where the image is given the object and the object and the value of the focal length. And two, we can just remember this right triangle that has the strict similarity ratio relationship. And we can get, after a little bit of algebra, the mirror equation. One over f equals 1 over d naught plus 1 over di. This could be positive or negative. And when we talk about convex lenses, this could also be positive or negative. And the second thing we have is we can put one of these negative signs back in. So it turns out that this is negative and this is positive, and that relationship's always going to be true. That di and hi are going to have inverted signs. So we have di over d naught with a negative is hi over h naught. So this and this are just a rephrasing of this similar triangle and the one that I didn't draw. But basically, it would proceed in the same way. Okay, so this is the numerical way of figuring out where my images show up. And what we'll do is we'll work through the convex cases, drawing the ray diagrams, and then putting in correct signs. But I just want to give you a quick example of how this would work. And again, the nice thing about all of these, like, doesn't matter what units you use. You may have been trained at gunpoint to use SI units back in mechanics, but as long as you're in the same units, millimeters, millimeters, centimeters, centimeters, and in fact, the same thing is true there, it doesn't matter. So just be consistent. You don't have to be SI. So I guess there's like one piece of jargon in this in some sense, is that describe the image would mean tell me where it is and tell me its magnification or its height. In this case, because we know how tall the object is, giving its actual height would be good enough. So I'm going to include, even though we have the mirror equation, I'm going to include another ray diagram because you can't see enough ray diagrams. And I'm going to draw it in such a way that we haven't seen it before, where I'm going to kind of mess with you about positive and negative, because positive and negative are not left and right in geometric optics. Positive and negative are defined by the object distance. And then we'll just dash through the math. Okay, so this is a concave mirror, and I'm going to not put its radius of curvature on there because I kind of don't care. The only thing I really need the radius of curvature for is to figure out where the focus is. So the focal length of any spherical mirror is half the radius of curvature. In this case, it's going to be on this side, so we'll put it at, or actually in some sense define 10 centimeters by this. Okay? And that means that my 5 centimeter tall object is placed 15 centimeters in front of that, so it's basically half over this. And it's 5 centimeters tall. Crazy enough, that's almost to scale, so that's wild. So the reason to use or do a ray diagram, and this is mostly what you'll use them for, is just kind of like a guiding light and sanity check, is that I'll really quickly sketch out a ray diagram, and that'll give me the general properties of what my solution should look like. It's not going to give me a precise answer, but it should be, like good enough. So ray 1 in parallel out through the focus. Ray 2 in through the focus. This is the thing that we won't really be able to do with a convex mirror because it's on the other side. We'll have to go towards it. And then ray 3 will be striking the center and then coming out. Okay. And it looks like they show up here. And again, I shouldn't dig too deeply into this as a precision instrument. But what I should do is this kind of gives me a sanity check that I should have a what type of image. So there are 3 things that I could use to describe it. Maybe you can pause and take a second and tell me how you would describe this qualitatively, no numbers. So real or virtual? Real, definitely real. The light rays actually converge there. Is it upright or inverted? It's definitely inverted. And then finally, because we went through at least these, there was a purpose in doing this, is that what I see is that because this is farther away, the height should actually be bigger. So this and this similar triangle would tell me that the magnification should be in absolute value greater than 1. So what I would expect to see is a magnification, lateral magnification of something like negative 1.2. Negative because it's inverted, and 1.2 because it's farther away. It actually won't be that, but that's what my picture indicates. Okay, so that's why we do ray diagrams. It gives us, kind of some qualitative guidelines. Okay, but now what we have is the mirror equation. And that will let me actually put numbers on things. Okay, so I know that the focal length is 10 centimeters. I know it's positive, so again, the sign conventions. For mirrors are that if it's on the object side, it's positive. So in fact, this is defined as positive. D0 is defined to be positive. F is also positive. That's always true for concave mirrors. And then also my ray diagram indicates that my DI should also be positive. So if I do this right, I should get 3 positive numbers. So 1 over F is 1 over D0 plus 1 over DI. So that's 1 over 10 cm, 1 over 15 cm, that's what was told to me, and 1 over DI, and then math happens, and I get, so what's that? 3/30ths, 2/30ths, 1/30th equals DI is 30 cm. So that's one of my 2 equations. That's the mirror equation. The part of the first triangle, the one that we drew that came out of the mirror equation, also tells us something else, is that minus DI over D0 equals HI over H0. And then we know that too, so that would tell me that the ratio of that to that, namely 2, is the ratio of that to that, so I should get a height of negative 10 centimeters. So twice as big in magnitude and flipped, okay? So in this, and I swear I didn't do this on purpose, you see the good and the bad of ray diagrams. One is that they gave us a lot of good qualitative information, right? The fact that this is definitely a real image, it's definitely inverted, and it's definitely far away than our object. As a precision instrument, you'd actually have to be really careful and use protractors and mirrors, right? So definitely inverted. Okay. So what we'll do is a couple of examples with this, and then we'll go through the entire procedure with convex instead of concave mirrors.